So let's get started. Today we're going to talk about node centrality and ranking on networks. So first of all, when you look at the network, there are certain nodes, nodes play different roles, and certain nodes look more important than others, or play more important roles, or are actually more central than others. If you look at this picture, right, which nodes, the vertices do you think are important here? Guys?
The largest.
Well, the largest, right? I actually, on this particular picture, I emphasize some nodes by scaling their size according to their degree. And so what you're literally saying is that the nodes with high degrees are important. Now, honestly, the good answer for this question would be like, what do you mean important, right? Important in what sense? If the importance are in the sense of number of connections or number of friends, yes, these are these large white nodes or vertices in the center of the graph. But there might be slightly different measurements or understanding of importance. For example, you can think about nodes as sort of geometrically important, right? So nodes being in the geometrical center of the graph. We're going to discuss in a minute what precisely I mean by that. But in any case, whatever sort of important metric, whatever metric of importance for nodes we introduce, this metric should satisfy certain constraints. And for example, if we want to measure the importance of the nodes just based on their position within the graph, right, on the connectivity structure of the graph, we're not looking at the context of the nodes themselves right now. Then if you look on the left-hand side and a graph on the left-hand side, the star graph, can you say something about importance of certain nodes on this graph, right? It doesn't matter, how we calculate that importance, but just by looking at this graph, can you say anything about the importance of some of the nodes?
Well, importances of these 6 nodes are the same, and the central node is more or less important.
Right. So due to symmetry, right, those 6 nodes will have the same importance. And by the way, this is also a good test for your algorithms later on when you start writing them, right? That's just to check for a very simple setup. Now, if I look at the circle on the right, what can you say about the importance of all those nodes?
Same.
Yeah, it should be the same, right? It's very symmetric. So they're all in the same sort of position within the graph, right? They should play the same role. So they're all have the same importance. Or if I look at the line graph at the bottom, probably nodes close to the center can be somewhat more important than the nodes at the periphery, right? At the edges, nodes A and G. But in any case, there is also symmetry in here. And so whatever the notion of importance we use, it should satisfy, some sort of symmetry and it should be meaningful when applied to this very simple graphs. Okay, so we're going to start with this 3 sort of basic metrics of node importance or node centrality. The first one is a degree centrality. So degree centrality is really just the number of nearest neighbors of the node, right? So it's a degree of the node. Now, very often we want to use a normalized centrality as a metric, and we're going to normalize it by, for example, we're going to normalize it by taking the node degree and dividing by n minus 1, where n is the number of nodes in the graph. Why do we do that? Why do we divide by n minus 1? Where did that come from?
It doesn't count this node?
Well, if we have n nodes in the graph and we pick up one node, what is the maximum number of connections this node can possibly have? in any graph.
N-1.
N-1.
-1, exactly. So that's what we do. We normalize it by the maximum possible number of connections. Now, why would we want to do it? Well, it's actually important if you want to compare the centrality of nodes between different graphs. Because if graphs have different sizes, right, then the centrality, if one graph has, 1,000 nodes and another has, I don't know, 10 nodes, right, then the node centrality, for example, 9, will be very large for one graph, for the small graph, but it will be very small for another, for the large graph. And so what you want to do is you want to normalize it, right? You want to know, then you can compare in between graphs. And for example, on this picture at the bottom, we look at the different nodes, and by looking at this, you realize that, for example, degree centrality. Which node has the highest degree centrality here? Pink or blue?
Pink.
Of course, pink, right? Yeah, this is high degree, right? There's like 1, 2, 3, 4, 5, 6, 7 neighbors for the pink node. But what I'm trying to say is you can have, several nodes in the graph with the same, degree centrality. It's okay. And those nodes not necessarily are kind of geometrically center of the graph, right? They can be located like on this picture. But then intuitively, the blue node is also central in some sense, right? So we probably need a different metric to emphasize, that will give us this blue node as the most central one. And that metric is called closeness centrality. And it's defined is how close a node or an actor, it actually comes from, by the way, these metrics, they come from social network analysis, from social sciences. And so that's why they keep talking about actors. But the idea is how close this node is to all other nodes, right? So what you do is you calculate the distance from the node. So I want to calculate closeness centrality for node I. Then what I do is I calculate the distance from the node I to all other nodes in the graph and add it up, right? So this is a total distance from the node to all other nodes. And the larger this distance, the smaller is the centrality. And the smaller the distance, the larger is the centrality, right? So in this case, for example, if I pick up this node, the distances to these 7 guys are small, but then this distance, then you measure this distance, then you measure this distance, then you measure this distance, this, etc., etc. So you get some number. Or, for this guy, it's the distance to these 3 guys, and then 2 steps away. And so in this case, the blue guy will have the largest closeness centrality, right? It will be the most central to the graph. So it's somewhat this geometric center of the graph. You also normalize it. If you want to get rid of the size or the effect of the size of the graph, but here, because it's in denominator, instead of dividing, we're multiplying by n by 1, right? Because we're measuring distances to n-1 nodes. Okay. Now, sometimes if the graph is disconnected, you might end up having, one sort of node disconnected, then it will ruin the entire metric. So then people invented, instead of just closeness centrality, so-called harmonic centrality. And the difference here is that instead of having distance in denominator and summing up all the distances and then taking inverse, you actually add up inverse of each distance. So it's slightly different metric, but it actually works if you have a disconnected graph, because it's only the node that is disconnected will not contribute in here. Okay, so that's sort of another option. Finally, there is also another very useful metric for centrality, which is called Betweenness Centrality. So the idea here is that, yes, there are some nodes, we can call them important or central if they are connected to a lot of other nodes, right? That's degree centrality. We can call node an important node if it is in sort of geometric center such that the sum of all the distances from this node to any other node is the smallest. Yet, you can think about the importance of the nodes as being bridges in the network, right? So think about, I don't know, St. Petersburg or Amsterdam and all the bridges. And so the bridges are important parts here. And so if you disconnect them, right, graph falls apart. And you can think of this also about this as say communication network. And let's say you have departments in the company, and that's communication among departments, and then the person who, for example, knows people here and there, and he will be a bridge. So he'll be important for that network. And that importance, that type of importance, is called betweenness centrality. The way to define it, calculate, is by calculating shortest path going through that node. So what I'm trying to say is this: we can pick up any node. Let's say I pick up this node, and I want to calculate all the shortest path from all the nodes in the graph that go that will go through this node. Right? Actually, I want to calculate all the shortest paths between nodes. So I'll pick up one node here, for example, one node there, right? This is shortest path that goes through this node A. This shortest path goes through this node. This shortest path goes through this node. Okay, shortest path from here to there doesn't go through that node. So the point is to calculate betweenness centrality for node I. We go through all the pairs of nodes in the graph, right? So from this to this, from this to that, from this to that. So go through all the pairs and calculate all the shortest path in between all the pairs. And then we also count how many of those shortest paths goes through the node that you selected. So in this case, if we're trying to calculate for node I, well, we calculate all the shortest path that goes through this node. And then this ratio will give you betweenness centrality. So for example, obviously a lot of shortest path will go through node A here, because every shortest path that goes from any node on that side to any node on that side should cross node A, right? At the same time, if you pick up this node, right, it's not all the shortest paths, it's only whatever goes to their neighbors will take this into account. So that method allows us to find the nodes of this type, sort of bridge nodes. Okay. Now, there is an interesting coefficient here. If we again want to do normalization to make sure this coefficient does not depend on the size of the graph, there is this number. What is this? Where does it come from?
It's number of paths of all paths from all of
Yep,
the
exactly.
vertices.
Yeah, so this is number of pairs. If you have n, so we have n nodes in the graph. We pick up one node. We want to calculate all the shortest path that goes through. Then there is n minus 1 nodes remains, and then we calculate total number of combinations in between n minus 1 nodes, a total number of pairs that you can form, and that's n minus 1 times n minus 2 over 2, right? And so that's where it's coming from. Okay, and so that's called normalized betweenness centrality, and again it emphasizes this shortest path, the fact that some nodes they positioned on the bridges. Okay, that's not all, right? So the next metric is even more interesting, and it has to do with that idea, with that simple idea that also comes, say, from the social networks world, that it's maybe not as important how many people you know as who you know, right? It is who you know, not how many people you know. So if you're friends with, I don't know, top leaders of the world, you're probably more important than somebody who has 1,000 friends of like nobody is, right? So how can you implement this idea in practice? Well, when since we only use network structure, in here, the importance is of course proportional to the number of connections. But what I'm trying to say is it's not necessarily the most highly connected node, not the one that has the highest node degree, is the most important, but it is maybe is that one that is connected to other nodes that are in turn important. So I made this sort of circular loopy statement. Node is important if it is connected to other nodes that are important, right? Surprisingly, you can express this statement mathematically, and you can actually solve it and find this notion of importance by just going from this assumption. So imagine that we call the parameter, say, vi is the importance of the node I. And then we're going to say is vi is calculated as the sum over all the neighbors, right? Aij is adjacency matrix, so it is non-zero only for the connections. So for example, if I want to calculate the importance of this node, what I do is I take the importance of its neighbors, right? Because these are neighbors. And so the importance of that node, of this node, is calculated as the sum, as a weighted sum, as importance of its neighbors. Now you would say, okay, yeah, sure, but in order to do then calculate this, I need to know these guys, right? How can you do that? Well, interestingly enough, you can by actually pretty much almost creating this, putting this into like this equation form, but there is one catch in here. And so what's the catch? So what can be a problem if I just set it up as an equation like this? So imagine that I assign at the beginning some importance values to all these nodes, right? Let's say I assign here 1, 1, I assign here, I don't know. Actually, I assign all ones to all of the nodes just to get started, right? Then I add this importance up, and let's say I calculate these numbers, and it's going to be 1, and it's 1, 2, 3, 4, 5, 6 neighbors. The importance of this node becomes 6. All right, fine. Then I want to recalculate importance of other nodes, these nodes. Then it's now this guy is 6, so the importance of those node will become, for example, 6 plus 1 plus 1 plus 1, so it becomes 9, right? And this guy becomes whatever, etc., etc. Then I come back and recalculate the importance of this node again, but now the neighbors don't have importance of 1, they have importance of like 9, 10, whatever. So it gets larger and larger and larger on each iteration. And so it just blows up. So just that simple thing will not going to work. But if on every iteration, after we add up all the values, we normalize it by some constant, right? So it's not just adding up all the importance of the neighbors, but we add up the importance of the neighbors, and we do 1 over lambda, where lambda is some constant. Then if we choose the lambda constant correctly, then this can become an equation that's solvable. And in fact, then we can rewrite it this way and solve it. What is this, guys? What do you call this? What's V?
Собственное значение.
It's eigenvector, right? It's eigenvector and eigenvalue. So then the concept is the following. If you want to calculate, and that's why it's called eigenvector centrality, right? So the idea is that you calculate, you take the matrix, your adjacency matrix, and you calculate its eigenvalues and eigenvectors. You take the eigenvector that corresponds to the largest eigenvalue, right? It's a vector. And then, there is an element in this vector for every node. And that element is importance of that node or eigenvector centrality. Does this make sense?
Yes.
Okay. Now, there is a very important point here, extremely important. this works only, this guaranteed to work, and in fact, this works only for undirected networks, only for undirected graphs. Why?
Because maybe A is not symmetric.
So because for undirected, it is symmetric,
Yes,
right?
and for directed it can be unsymmetric.
Exactly. For directed, it's unsymmetric. For undirected, it is symmetric. And if it is symmetric, it's guaranteed to have orthogonal eigenvectors and real valued eigenvalues. It's not true for unsymmetric matrix. And so you cannot use this method over there, but we're going to actually discuss in the second part of the lecture what you do with directed graphs. All right, so this is eigenvector centrality. So again, the idea here is that your importance depends on who you know, right? Your importance depends on the importance of your neighbors.
Does it works with negative values in matrix I?
Ooh.
Or just
It's a good question. Typically you look at the matrix, which is a binary, right? Which is connections. So it's 0 1s. Now I'm actually don't remember if the matrix has negative values. I mean, I don't remember what it takes for a matrix to. I think it's positive definite, right? In order for it to have all non-negative eigenvalues, all non-negative entries in eigenvalue, in eigenvector. I'm sorry. But I typically you don't meet this type of situation. You typically have either binary graph 0 1, or you have non-negative weights. Anytime you have negative weights on the graph, it becomes much harder, because then the notion, for example, of shortest path also breaks down, right? Because if you have weighted shortest path, then you don't have a shortest path, right? Because then the shortest path becomes, if you have negative weights and you take them into account. So it's become, I'm sure there is a nice way out, but you have to be careful. And, in practice, you really never encounter that situation.
Can I ask a question
Sure.
about this? So as I understood, for example, if we have this Nancy node, and for example, hypothetically, it is connected only to nodes with degree 1. So Nancy will not be important in this paradigm if it is connected to only 1 degree nodes.
So see, the question here is, it's not
but
only
a lot of them, for example.
Look, but that's actually the interesting part here, right? The way we define importance here is not just the number of connections, but the importance of connections. For example, if Nancy is connected to a lot of to a lot of not very important nodes, it increases her importance, right? But then somebody else who is connected to 2 or 3 important nodes might have even higher importance than she, though she has many more connections.
Mm-hmm.
Make sense?
Yeah. I just wanted to make an analogy with real life. For example, one person has a lot of subscribers, but they're not
They're not
how
famous.
to say. But these subscribers don't have a lot of subscribers.
Exactly.
So this person is not important in
Yeah,
this.
exactly. So
okay, got it.
This takes, so if you just talk about the degree centrality, then if somebody has a lot of subscribers, it doesn't matter who those subscribers are. The degree centrality will be large, and he will be important in terms of the number of subscribers. But if those subscribers are nobody, right, and they don't have any other subscribers, then, so this is actually more nuanced, more subtle measure of centrality. Okay. So this is here are just a few examples. Now, if I look at this graph, these are the nodes that we highlighted, the nodes that have the highest closeness centrality, right? It's maybe not very easy to see, but they are kind of, all of them are in the center of the clusters, right? Which, groups of nodes that are tightly connected, which makes some sense, because Again, closeness centrality is a centrality that is measured as the sum of the inverse sum of the distances from the node to all other nodes. So the more nodes, the more the tighter the group of nodes the node belongs to, right? The more connections in there, the probably, the more nodes it has shortest path to, right? And the higher its closeness centrality then. So that's closeness centrality. Now, if we think about betweenness centrality, which nodes do you think will have high betweenness centrality in this picture?
The hubs between the clusters.
Yeah, those guys, right? The sort of bridges, the nodes you get, you get this, all the nodes connected to this and everything else, so through these guys. So that's probably the guys. Okay, let's see. Yep. So these are the largest betweenness centrality. Now, the difficult, challenging question: which nodes will have high eigenvector centrality, right, or eigenvalue centrality? Which nodes will have high centrality of that type? That's not an easy question. So remember, when we talk about eigenvector centrality, it's the centrality of the node, eigenvector centrality of the node, depends on the centrality of its neighbors, right? So if whenever those nodes with high eigenvector centrality located, they should be next to each other, right? They kind of, because they enforce each other, right? They enhance each other. So I actually don't know the right answer. I don't remember it, but I would guess, maybe either this group of nodes can be high, or maybe this group of nodes. But in any case, they should be next to each other. So let's see. Okay, yeah, that's where they are. So this, if you actually calculate for this network eigenvector centrality, these are the guys who will have the highest. All right, make sense? Okay. Now, there are, in fact, many more centralities that has been invented, and one of them is just sort of FUI, right, for your information. That's the centrality invented by, for example, sociologists. It's called Katz, status index, or Katz centrality. And the idea is that what we have done so far, for example, in degrees, or I mean in betweenness centrality, or what we have done in other centralities, is we calculated the shortest path from the nodes, right? So what the Katz centrality is doing is actually saying that centrality depends on the nearest neighbors, right? Aij is the nearest neighbors. Aij squared, this is actually second order neighbors, because when you take the matrix and squared it, the non-zero values means which nodes are 2 steps away. And these are the third degree value. I mean, the cubed, it means 3 steps away, etc., etc. And so what it says, okay, let's take different weights. Let's let's put a weight beta on the importance of the direct connections. Then we'll take beta squared as an importance of the second degree connection, so second step connections, right? Second degree connections, so 2 steps away. Then let's take beta cube for those that are 3 steps away, and so on. And beta is less than 1. And so, which means the nearest neighbors are more important, right? Then those are important but less. Then there's less, and less. And so then, if you do that, you can show that if beta is less than 1 over lambda 1, where lambda 1 is the first eigenvalue, the largest eigenvalue of the matrix A, then this whole thing, the sum converges. So you can actually calculate it for the entire graph, and there is a closed form solution. Now, you probably will not see a lot of this in practice, but this just shows you that there are many other forms or logic, or behind the centrality ideas, and you can come up with your own metric of centrality. Call it your name, Andres centrality, or whatever, right? And then just run with it. Just explain to people why it's important. and what it measures, right? So, if you look at this example, this is called a geometric graph. That's why it's sort of a little bit strange, but it kind of highlights some of the ideas of the centrality. Notice node A, the Betweenness centrality. So, I'm sorry, not A, but figure A. This is Betweenness centrality, and we can see here this color is bad. We can see here those bridges that are highlighted. They have the highest Betweenness centrality, Closeness centrality. This is, as we expected, is a geometric center. Eigenvector centrality is slightly different. It's actually very hard to predict it on this graph, but important that the nodes with high eigenvector centrality, they're all next to each other, and the rest have very low. So notice is if you look at the Closeness centrality, that sort of metric is distributed, right? In the sense that, yes, these are red, but then the color slowly drops to the edges, right? With eigenvector, these are very focused, right? So there is some nodes that have it high and then the rest have it low. Then there's degree centrality. Well, here it's hard to see, but like nodes are randomly scattered and all of them have similar node degrees. Then harmonic centrality, remember, this is one of the options how you do centrality, how you do closeness centrality. That's why the picture is very similar. Slight differences. And then the Scott centrality we just talked about, it actually manages to pick out those nodes. So it's just an example that different centralities, call different nodes central. And so when somebody asks question like, okay, which nodes are important? Well, you need to clarify what do you mean importance is, right? Is it number of direct neighbors, number of neighbors you can reach in 2 steps? Is it, what's important, who your friends are, right? Not how many you have, or is it geometric, blah, blah, blah. So there was like lots of options here, okay? All right. Any questions on this centrality story? All right, let's move on. Then we're going to switch to directed graphs. Now, as I already mentioned, directed graphs are different in terms of the centrality stories. And what's so different? Well, there are a couple of things different here. So first of all, there are some obvious things. When we have a directed graph, we have some nodes that are called absorbing nodes, or sinks. These are nodes that do not have out degrees, right? So there are only arrows going there. And if you think about the graph as a sort of one-way streets, right? This is sort of dead end, right? You get there and you cannot get out. So that's important. If you consider, for example, walk on graph, or like sort of randomly following the arrows, if you start, say, from here, get here, and then get there, you're stuck. You cannot live, right? So that's a sinks. Then there is another kind of nodes that are sources. And source node is like this. Nothing comes to it, but only leaves, right? So if you leave this node, right, there is no way to get back. And there is no way to get to this node unless you started in that node. Finally, there is this always challenge in terms of determining and defining distances. For example, I want to calculate the distance in between node 2 and node 3. All right. So in between node 2 and node 3, it's one step if you go from 2 to 3. But from 3, you cannot get to 2. So the distance is infinite. So it's not going to work, right? Or, for example, distance from node 1 to node 2. Let me clear this out. The distance between node 1 to node 2, so distance from 1 to 2 is one step, right? But distance from 2 to 1, I want to go back, right? is 2 steps. So all of a sudden, it screws up the notion of distance for us, right? It's like on one-way street. You know, getting from one point to another can be like very quickly, but if there is no parallel return streets, well, you need to go all the way around to get back. And so that's why metrics that are based directly on distances are actually hard to use on the directed graphs, because they might be misleading, right? Because of this sort of phenomenon that on directed graph, you have this one-way streets, right? And the distance from one node, the distance becomes not symmetric, right? So from one node to another is not equal to the distance back. And then the question is like, what do you actually call distance? So that's why typically on directed graphs, you do use, you do use degree centrality, and that becomes sort of in degree and out degree centrality, right? Two centralities for a node. But closeness centrality and betweenness centrality has this challenge of distances depending on the way you go. And so you have to be very careful if you're using them. There is a bunch of literature if you want to learn how to use them. Very often, what we do is we just take this directed graph, we drop the directionality of the graph if we actually want to pick up the nodes that are most sort of central, or the bridges, and just calculate that as for undirected graph, right? And use it as a proxy. But again, you can compute it technically, but it might be misleading, could be misleading. So then what do you do for directed graphs? Well, before we jump into that, let me remind you a couple things from graph theory, which we need in a few seconds. So graph is called strongly connected, is every vertex is reachable from any other vertex, right? So remember, in undirected network, graph is connected if you can reach from any vertex, any other vertex. Graph is strongly connected for directed graph if, again, every vertex is reachable. Directed graph can be connected, but not strongly connected, right? Let me give you an example. This one is connected because if we remove arrows, if we remove directions, you can get from any node to any other node. But it is not strongly connected, because when it is directed, right, when we look at it as a directed graph, you cannot get from node 2 to node 5, for example, or you cannot get from node 4 to node 2. So it's not strongly connected, okay? Now, strong connectivity does not mean that you necessarily need to have, both ways from 2 nodes. You can get sort of maybe other way around through other nodes, but you should have a way. And on this graph, again, for nodes like 4 or 5, there's no way, in one case in, in another case out. All right, now you can take a graph and divide it into strongly connected components. Then it means within each component, like here, you can get from any node to any other node. And notice it's directed graph, so you can get from A to B in one step, but you can get back. But it will take you 2 steps, but you can get back. The same thing in here, the same thing in here. But if you ended up coming, going from B to C, getting from this component to this one, you will never get back. So that's strong connectivity. So another important for us notion is periodicity. Now, here I'll slow down, read the statement. I'll give you a few seconds for this to sink in. If you never met this definition, it's a little bit hard to understand, but the idea is the following. So graph is a periodic if the greatest common divisor of the lengths of its cycles is 1. What in the world is it trying to say? Well, what it's saying is the following. Look, graph can have cycles, right? There is a cycle here, this one, and this one. So now this cycle has 1, 2, 3, 4, 5, 6. The length of the cycle is 6. And the length of this cycle is 5. So the greatest common divisor is what? Is 1.
1.
Yeah. And that's why it's a periodic. Now, if I look at this graph, look, 1, 2, 3, 4, 5, 6. And here, 3. And here, 3. And here, 3. What the greatest common divider?
3.
3, right? So this graph is periodic. Like intuitively, what it means, you have loops here that, you know, can be sort of, well, it's hard. It's actually, you know, probably this greatest common divisor is the easiest way to explain it, right? But you can take, you know, one loop and the other one will be the integer times that one, right? Or you know, something like that. But again, to make it precise, you need to talk about common dividers. So why is this important? Why is this important? Well, this is important because sometimes when you calculate certain properties in the graph where you have iterative process, iterations, right? You know, multiply matrices iteratively. If you have loops in the graph like this and the graphs are periodic, then those calculations will never converge. And there is mathematical proof for it. And it's only for this type of graphs when things always converge, certain iterations. Now, it's actually very easy to make any graph aperiodic by, you know, how can I, with extremely simple trick, how can I make this graph aperiodic? Now it is periodic, right? And it's period, here it's period 3, right? But how can I make it aperiodic with adding just one link? What I can do, I can, for example, say, okay, let's add this edge, right? Like a loop to any node, doesn't matter. Because then we get a cycle of the length 1, and then that's it. It becomes aperiodic, right? Because all of a sudden, yes, we have a cycle of length 6, we have a cycle of length 3, and we also have a cycle of length 1. Now, the reason I'm actually trying to pay, you know, to spend so much time spending so much time explaining this is because, you know, this is one of the reasons you need to do certain modification with the graph so the algorithm works. Yeah, the good news is that it's done with algorithms, and so you don't need to worry, but it might explain to you a few things later. So where did the algorithm came from? Well, those algorithms for directed graphs, they, you know, one of the ideas and the most sort of powerful algorithm came from the notion of ranking of web pages. And if you know that web pages are, well, pretty much, you know, hyperlinked, right? And the page points to other pages, and those hyperlinks from one page to another page, from one page to another page, they, you know, eventually forms an endorsement. I'm sorry, they form a web graph, right? Sometimes there is reciprocity, right? So there is this page linked to that, and the other page is linked back. Sometimes not. But that's what web graph is. And so, you know, if we go back 20 years, you know, the times when the Google started and other companies that worked on the web, there was a problem of search engines where, you know, the original search engines were only looking at the text and returning queries. But unfortunately, just looking at the text will not give you the best quality because there's a lot of pages that, you know, kind of either copycats, or there are pages that maybe, you know, have the same words, but not very, I mean, not the sort of not correct, not important. You cannot trust them. And so the idea was to actually use the structure of the web to find out which pages are important. And the reason it would work is because people build those pages, I mean, and can connect to those pages, put those hyperlinks. So in some sense, people who connect, a person who connects his page to some other page is endorsing it. It's just saying like, look, guys, I am connecting to that page and I think it's important, it's correct. And if there are some pages that has a lot of connections to it, then that page is good, right? But then if we just do that, we'll end up having this problem of somebody who is nobody, right? Some pages that are not important endorsing other pages, making them important, right? And that's not what we want to do. And so then you need to use some sort of eigenvector type of calculations, right? What we did previously. But the challenge is that just eigenvector centrality is not going to work here, as we discussed before, because the graph is undirected, and so you just cannot calculate that. So what would you do? And the solution actually came, like sort of historically, we believe that was the beginning of Google, right? When Sergey Brin and Larry Page, they proposed and published paper on PageRank. And the idea is that, we want to rank pages. And we want to rank pages based on those connections. But, how can we do this? Well, the idea is that we're going to use the model, so-called model for random surfer. Who actually sort of a random surfer is a person who start at some page and then follows links, right? Goes to another page. That page might have other outlinks, while the person will follow those outlinks and just keep walking around. Then at some moment, he might end up getting to the page when there is no outlinks. So what he would do then? Well, he would then just randomly jump and start surfing somewhere else on the web, right? And that's what they call this sort of random surfer behavior. So, and there might be also a slightly different pattern that, he still surfs, he goes from one page to another, but then he stops. I mean, there might be still outlinks, but he just wants to start a new search and go somewhere else. Again, 20 years ago, when the web was very new, people actually done that. Today, it's probably you don't do it. You just go directly to the web search what you need. But you can think of a little bit of behavior on a social network. I'm sure you've done it also when you pick up, you go to your friend's profile and then there are his friends and you're kind of interested in somebody's, I don't know, picture. You click on it, you go to the friend of friend, and then you just go to a friend of friend of friend, and then you just sort of walking around until you realize that you're looking at someone you have no clue who it is, right? And then you go back to your sort of your page, right? Your page in social network. So, but that's this random surfer. And mathematically speaking, what happens is that within this model, you follow the links, right? The actual links, the actual edges, which are shown here in gray, right? Follow actual edges, actual hyperlinks. But then you can also kind of come back by hitting the back button, or you can sort of jump randomly to any other page, right? Or you can reload the page. So, okay, that's the model. Now, how can we express, and then the guys proposed it, calculated it based on this model, and we're going to see in a second how they put this into mathematical formulation, and it actually worked. It worked tremendously well, and that made this PageRank insanely popular. And of course, Google is not only about PageRank; it's also about startup, about luck, about good management, engineering, etc., etc. But historically, yes, this algorithm is a founding sort of algorithm for Google. Okay, so how do we calculate this PageRank thing? Well, let's just look at the example. So what we want to do is we want to calculate the probability of being at the node at some moment of time. Let's say I want to calculate the probability of being at some node at moment of time t+1. Let's say I want to calculate probability of being at the node 3 at t+1. In order for this random walker to be on the node 3 at time t+1, on the previous time step, he should be either here or there, right? Because there's no other way to get to number 3. Okay, then if the worker sits on the node 1 previously, then he has two options. He can go to node 2 or to node 3, so the probability to follow one of the links is 1/2. If somebody sits on the node 4, then the probability to get to node 3 on the next step is 1, simply because there's no other options for number 4. So probability of being a node 3, we can calculate it as, and this is t+1 time step, is probability of being at the node 1 times 1/2, because that will takes it, that the chance to get to 3, plus probability of being at the node 4 previously times 1, because if somebody was at the node 4, there's only one way out, which is node 3, right? And this is this formula. So you calculate probability of being at the node I at time t+1 as a combination of probabilities being on its neighbors divided by the degrees of those neighbors. And you can also write it down, since here I'm summing over neighbors. Well, you can actually write it down as a sum with their adjacency matrix. And if I want to write it in terms of equations in the vector form, in the matrix in the vector form, that's what it's going to look like. It is probability of being in the node t+1 at the time t+1 at any node is calculated as taking the probability of being on any node at the previous moment of time times this matrix, or it's called transition matrix. And that's pretty much it. Now, that's sort of wonderful theory. Now, the problem is it's not going to work for this graph. And the reason it's not going to work for this graph is because if I start doing these random walks, what's going to happen is, actually, you tell me, guys, why it's not going to work. Why this sort of iterations is not going to work for the graph A. What's wrong with graph A?
It cannot be inverted because vertex 2 has no out degree. It has
For
0
example,
out degree.
Yeah. So what's going to happen is if I start walking around, as I described, and you get onto the node 2, you cannot leave, right? You're stuck there. Or, you can never get to node 1 either. So that's a challenge. But it's going to work on this graph, right? Because here, though it looks very complicated, right, in a lot of one-way streets, but from any node, you can get to any other node and come back, right? So, and the reason this graph, it's strongly connected, and that's why it works. So in order for this thing to work, we need to make this graph strongly connected. To do this, we need to sort of artificially add some ways to get to the nodes where you couldn't get, and get some ways to get out of the nodes where you couldn't get out. And now, remember, we just talked about this random surfer. This corresponds to the idea that, okay, you got to the page where there is no way out. Well, you randomly jump to some other page in the graph. To do that, you need to have a connection, and this is sort of virtual connection that allows you to jump there. But for the graph, yeah, it's going to be a connection there. Does this make some sense?
Yes, yes.
Okay. So, of course, we don't want to modify the graph, right? Because the graph is huge. But instead, what we can do is this. We can take, when we do iterations, right? And let me show you back. So that's our that's our iterations that we wanted to do, right? Where this is the adjacency matrix, which is normalized by out degrees, right? There's the inversion thing. Okay, so what we do is this. Instead of just taking this part, we'll add another part. And this another part is actually has a meaning of this random jump to any other node. So what this says is the following. With this probability alpha, you follow the graph. But then with 1 minus alpha, you actually can jump to any other node in the graph. E is a unit vector that is a vector of all the nodes. And so what this literally says is the following. If I go back, it's probably easier to show on this graph. What this says is the following. Yes, we have these connections and we follow that with that alpha probability. But with 1 minus alpha, we can actually, from any node, we can randomly jump to any other node in the graph. So if from node 2, we can jump to 3, to 4, to 1. If from node 3, we can jump to 2, we can jump to 1, we can jump to 4. If it's node 4, we can jump to 1, we can jump to 3, we can jump to 2. It has small probability, but we can do it, right? The actual connections do not exist, but we can do it in this sort of virtual formula world, right? And these are those power iterations, right? Again, this is the following the links, and this is this teleportation, what it's called, right? Well, teleportation because, it's jumping from one page to another when there is no direct connections. Typically, this alpha that is used in practice, or has been shown to be efficient, is 0.85. So it is 85% that you follow the link, and 15% that you do this random hop. And then when we're done with this, we have this power iterations written. You can actually solve it as a linear system, and you can solve it eigenvalue problem. And notice again, it's an eigenvalue problem, the same the same type of problem as for eigenvector centrality, right? It's eigenvalue eigenvector problem, but it came from a different discussion. It came from this notion of random walks, and we're not using just matrix itself. Here, there's this combinations of sort of the matrix, then we're normalizing by out degrees, then we're adding this unit matrix for the random jump. And that's what makes this work. Without it, the original matrix, remember, is unsymmetric. It has sinks and sources. And so sometimes this will not be invertible or some other things. But we're fixing it by doing this. And in fact, this fix works surprisingly well. And the reason it works is because of so-called Periodicity theorem. It's a fundamental theorem of Markov chain. And it says that if the matrix is stochastic, and stochastic means it's non-negative and rows sum up to 1. And in our case, yes, that's a transition matrix, and that's what it does. It's irreducible, right? So the graph is strongly connected, and that's what we have. Remember, by adding those jumps, we create a strongly connected graph, and aperiodic, so there is no loops that are that common denominator is different than 1. Then there is a limit, so there exists a limit, and it can be defined as an eigenvector. So again, the point is the following. You have this graph, you randomly jumping from one page to another, and then you calculate the probability that after this long walk, you end up on a page. And that probability is called page rank. And this is, mathematically speaking, this is the distribution. This is the probability of a random walk, it exists, and it's a stationary distribution of a Markov chain that corresponds to this graph. So again, the idea is you have a graph. You start from some point. You walk the path. You walk the edges until you get to. And then it's never-ending walk. Remember, that's why we want it to be strongly connected, so it never gets stuck. and just you keep walking. And you calculate literally how often you visit each page. And then you normalize this and you get the probability of visiting the page. And then you rank those pages by that probability. And the highest probability will give you the largest page rank. So the idea also may be kind of, if you want to have an analogy, think about you being in a city with one-way streets, and you kind of randomly walking in the city. It's an old town. I don't know. Think about, I don't know, Vilnius or any European small town, and you go to the squares. You change. You randomly pick up the street to follow. You follow that street, and you just keep doing it all day long. And you start noticing that you kind of coming to some of those squares, some of those intersections more often than others. And if you calculate how many times you get there, and then normalize by the total number of squares you visited, that will be your PageRank score. Now, you can calculate this like literally explicitly by simulating it on the graph, by just like sort of simulating random walk, by following the link and randomly picking up the other direction, just keep going and counting. Or you can do it by solving this equation, right? The PageRank equation. Of course, nobody does the simulation unless you want to calculate local PageRank for the local neighborhood. And what you do is you usually solve it as an eigenvalue problem at the power iterations. And so that's a famous PageRank. I'm going to stop here for a second. Any questions? All right, we kind of jumped from very simple stuff to quite complex stuff. But the point is, if you have directed graph, this is a graph where we calculated PageRank for different, for all the nodes, and the nodes are scaled according to PageRank. And the same way as with Eigenvector Centrality, it's not necessarily the nodes that have the largest node degree they will have the largest PageRank. It really depends on the connectivity pattern of the graph and how often on this random walks you will be going back to that particular node, through that particular node, and that's a PageRank. And that scoring mechanism, the way to kind of rank the pages, is so powerful, and it's actually so robust that people has created tons and tons of other sort of PageRank inspired ranking mechanisms on the network. There's this gene rank, trust rank, bad rank, impression rank, Twitter rank, pop rank, site rank, you name it rank. And for each of those ranks, there is a sort of there's corresponding matrix, right? And the corresponding graph, and you try to rank the pages based on this PageRank algorithm. It just has different meaning depending on what your graph is about. If it's, for example, citation graph, you get site rank. If it is, investor graph, who invested where, it's investor graph, and et cetera, et cetera. And I think I give a reference at the end for the page that describes, for the archive paper that describes a lot of this, lots of this ranks, page ranks. But the point is, if you want to rank something on a, on a directed graph, if you want to rank nodes on the directed graph, you use PageRank, period. Okay, now the story will not be complete without mentioning another algorithm which is called HITs, or Hubs Authorities. It's actually a very interesting idea. It didn't take off, and it's sort of, the algorithm doesn't work too well on a very large graphs, and I think that's one of the reasons it didn't work out for the web. But the idea by itself is kind of cute, and so it's worth knowing about it. It's also for directed graphs, and the idea comes from, it's probably easiest to understand on the citation literature. So when you take papers, the papers usually, usually write papers as they're papers that are reviews, and they're papers that are sort of original research. And the idea is that good review papers, they do point to good research papers, right? And in turn, good research papers point to good reviews. So you have this notion of connectedness in between, good research and good reviews. And every paper contains some review in it. And so every paper can be characterized by those two numbers. How good review it is and how good is the original part of the paper is. Now, I brought this as this reviews versus original papers. The way this work has been introduced, people talk about hubs and authorities. So authorities are those nodes that you can think of as a sort of authoritative for research papers, and hubs are those nodes that are connectors, literally. And so every node has two scores now. Instead of one score, instead of this page rank, it has two score. It's a hub score and it's authority score. And then you can calculate based on those two scores. You can actually calculate. You can calculate two metrics, right? And so the idea is that good authorities are usually referred by good hubs. And so this authority score is calculated as the sum of the hub score of its neighbors. Notice when you see this kind of circular logic, it's always end up in being sort of in becoming eigenvector, eigenvalue problem, right? With eigenvector, eigenvalue, eigenvector centrality, we talked about the centrality being the sum of its neighbors times the centrality of those neighbors, right? Or importance. Here we're saying slightly different. We're saying, the the authoritativeness of the node is equal to the sum of the hubness of its neighbors, and the hubness of its neighbors is the sum or the authoritativeness of its neighbors, right? So we kind of introduce two flavors here, right? So every node gets two scores, A and H. A and H. Every node has two scores, but when you calculate A score of this node, you use H score of neighbors pointing to it, right? And other way around. And if we look at those two equations, we can in fact convert them again easily into this eigenvalue eigenvector problem in this form, right? So we're going to have a system of linear, we're going to have this two systems of linear equations. And what's interesting that, because we have those two equations, right? This is, we're saying, authoritativeness is calculated from the hubness, and then hubness calculated from authoritativeness. So you can plug this in here, and then we can get, two systems, each of them can actually is completed. And notice, it's now A transpose here. Now, why is this important? It's not the matrix A itself now. It is A transpose. Why is that important?
It is positive semi-definite.
Exactly. Because remember, the matrix A was directed. It's a directed graph, and so you could not just do eigenvalues, eigenvectors in it because it's just cannot, right? It's not guaranteed to have positive eigenvalues. This one is positive semi-definite, so it's guaranteed to have real and actually positive eigenvalues. So that is sort of converts again non-symmetric. So pretty much what's been done is in PageRank, we took this unsymmetric problem and modified the matrix to those random jumps. Here, we took it and modified it by doing AA transpose and introducing those two levels of scores. So it actually works quite nicely when you run this. You realize that, yeah, so the nodes that are connected, like the connectors, the hubs, they're actually getting pretty large hub score. And on the left, the size of the nodes are proportional to the hub score. And on the right, it's authoritativeness score. And you see that some of the nodes here get high authority scores. Well, some gets low, but notice these guys have high authority score, and they're pointing, this guy, the central one, has low authority score, but this have high authority score, but they're pointed to the guy with large hub score, right? So this guy has large hub score. This guy's this is the same, right? They have low hub score because obviously they're not pointing to anybody, but they have high authority score. And so this is enforces this notion of that high hub score, points to high authority score. Okay. And so, if you think about if for whatever reason your problem, you have this field that in the graph you need to, separate and introduce two different metrics like hubs authorities, right? Again, it's sort of citation, original papers, review papers. Hubs authorities can be a good algorithm. Now, unfortunately, it doesn't work too well for very large graphs. There are some reasons for that, but for the networks, up to thousands or several thousand, it works pretty well. So I encourage you to try it, if you're interested in this type of stuff. And yes, and with that, we're done. So there are more references here, starting from the centrality and going back to 70s, 80s, 53, right? That's when people talk about a lot about centralities and sociology. And the stuff with PageRank citation, this is 98. In fact, this is the classic page by, Larry Page, Sergey Brin, with their advisor, Terry Vinograd, and Rajiv Madhwani, the PageRank, right? That sort of started this whole thing, started Google supposedly. And, this one is a David Gleich review if you're interested in, very different applications of the PageRank. And with that, we are done. Any questions? All right, no questions. I know you're going to have a seminar in a few minutes, so let's have a quick break, and then please join that Zoom meeting. Thank you.
Thank you.